So if you were absent from class the last day or so, you missed a lesson where I went over how to translate the quantum number stuff into things called electron configurations and orbital notations. So I'm going to do that by going over U5.5 P1 Electron Configurations. It's the second to last worksheet in your packet. And I'm going to go over the first three atoms on there, and then we're going to talk about how that relates to the periodic table, and then we're going to talk about how that relates to valence electrons. So if we start with the first one, which is magnesium, magnesium on the periodic table has an atomic number of 12. Which means that it has 12 protons, but it also has 12 electrons. So now we are going to refer back to this document, or to this diagram in the beginning of U5.5 N2. And so this diagram right here is a visual representation of how electrons are placed around the nucleus of an atom. So if we imagine that the nucleus of the atom is right here, so here's my nucleus of my atom, we have energy levels that are closer to the nucleus and energy levels that are further away from the nucleus of the atom. So the energy levels first always start with the first energy level, then the second, then the third, then the fourth, fifth, so on until we get to 7. But the other thing that we have to remember, that according to the notes, is that the first energy level has one sublevel that happens to be S-shaped. The second energy level has two sublevels, one is S-shaped and one is P-shaped, and the third energy level has 3 sublevels, one that is S-shaped, one that is P-shaped, and one that is D-shaped. Now, the other thing that you need to remember is that each of these dots or circles here represent the capacity to hold 2 total electrons. So the S-shaped sublevel always can hold 2. The P-shaped sublevel can hold 2, 2, 2 for a total of 6, and the D-shaped sublevel can hold 2, 2, 2, 2, 2 for a total of 10. Now we're going to come back to this diagram multiple times as we walk through this, but the first thing I want to talk about is electron placement for magnesium. So magnesium, we've said that has 12 electrons, so we have to figure out where to put our 12 electrons. So I'm going to start with the 1s, the first energy level, and I'm going to write that like this. So I'm going to write 1s, and then I'm going to add arrows. So arrow up, arrow down. So the other thing I want to make a point of is that one singular arrow equals 1 electron. So after I've used 2 of the 12 electrons that are present in magnesium, I'm going to go back and refer to this diagram and see that I've completed the first energy level. So now I'm going to go to the second energy level. The second energy level has a 2s sublevel and a 2p sublevel. So I'm going to represent that with another drawing. So I'm going to draw 2s and 2p, 2p, and 2p. So my 2s, again, can only hold 2 electrons, so arrow up, arrow down. Now my 2p, the reason why I wrote it like this is because in this diagram there are 3 circles. Each circle can hold 2 electrons. But I kind of want to make the point that in 3-dimensional space, you have like a px, a py, and a pz. It's not exactly that, but that's kind of how we think about it in terms of like geometry, where you have like that scale where it's like the x, y, and then something like that. Or maybe I drew it backwards. I don't know. So this is like z, x, and y. I think I drew this backwards, but the idea is still the same. So now at this point, I have used 4 of my 12 electrons. So I'm going to continue to add electrons, arrow up, arrow up, arrow up, and then arrow down, arrow down, arrow down. So I placed 2, 4, 6, 8, 10 of my 12 total electrons. So now I'm going to go back and look and see what will come next. So I did 1s, I did 2s and 2p, now I'm going to go to 3s. So I'm going to use 3s, and I'm going to go arrow up, arrow down, And at this point, I've used 2, 4, 6, 8, 10, 12, and I've just drawn what's called the orbital notation. Okay? And then, so this fills in the first row in the top half of that worksheet. So now we're going to skip to the first row of the bottom half of that worksheet, where we are going to translate the orbital notation into something called the electron configuration. The electron configuration is very similar. It uses numbers, letters, and superscripted numbers, whereas the orbital notation uses numbers, letters, and arrows to represent where an electron is. So I can translate this into 1s. I've got 2 arrows, 2 electrons, 1s2. I can translate this into 2s, 2 arrows, 2. And now this will condense into just simply 2p, 1, 2, 3, 4, 5, 6, 2p6. And then lastly, my 3s will look something like this. So this is the electron configuration. So in terms of identifying approximately where an electron is located, both of these ways to represent electron location are pretty accurate. However, this one might be slightly more accurate because I could probably talk about the one specific electron maybe in this particular 2p orbital of the 2p sublevel, whereas over here it just looks like there's 6 of them, and that might be a little bit more general, which is okay, but you have to be able to do both of these skills. So now we're going to move on, and so this is the top half of the worksheet, this is the top of the bottom half of the worksheet. So now we're going to move on and do our next one, which according to the worksheet is phosphorus. So I'm going to grab my periodic table. I'm going to locate phosphorus over here. Phosphorus has 15 total electrons. So it's because its atomic number is 15, which means it has 15 protons and 15 electrons. So I'm going to go back to looking at this diagram, and I'm going to always start at the first energy level, which is the 1s. So I'm going to draw my orbital notation, which would be 1s, and I'm going to go arrow up, arrow down. So I've used 2 of the 15. So after 1s comes 2s and 2p. So I'm going to draw that. 2s, 2p, 2p, 2p. Each dash or circle can hold 2 electrons. So I'm going to go ahead and do that. Arrow up, arrow up, arrow up, arrow down, arrow down, arrow down. And again, I've used 2, 4, 6, 8, 10 of my electrons. So now I'm going to go on and see what would come next. So I went 1s, first energy level. Second energy level was 2s and 2p. And then the third energy level is 3s, 3p, 3d. And we'll talk about why 4s is an overlap here in a moment. But I'm going to go start with my 3s and my 3p because I might not need to go much further than that. So I'm going to go 3s and then 3p, like so. So I'm going to go arrow up, arrow down. So 2, 4, 6, 8, 10, 12. So I've got 3 more electrons left to place. And now I want to talk about why I'm going to draw these the way that I do. So I have 3 electrons left to place. And what some people would want to do is they would want to go arrow up, arrow down, arrow up, like so. And I'm going to tell you that that's actually not correct. And the reason why that's not correct has to do with the analogy that I play with, or that I say was when I talk about like when my wife and I potentially get into an argument. When my wife and I potentially get into an argument, at some point my wife says, I need you to go away from me right now. I need some space. So she'll go upstairs and she'll sit in our room and watch TV or scroll on her phone for a little while, and I'll go outside and take a few deep breaths, and a little while later we can come together and have a conversation when we're not negative. Making the point of being not negative is really important because electrons are negatively charged. So when you take 2 negative things and you put them together, that generally doesn't go well. Like, think about it like this. If my wife and I got into an argument and then we'd got in a car and had to drive 2 hours in the car together, that fight would probably get pretty nasty. So what I'm getting at here is that electrons are also negative, and we try to separate them out like this. Arrow up, arrow up, arrow up, before we force them to be together. And so when you're writing your electron configurations, if you can spread them out, arrow up, arrow up, arrow up, before you go arrow up, arrow down, you want to try to do that. And in this case, this example does exactly that. Arrow up, arrow up, arrow up. I've used all 15 of my electrons. So my orbital notation for phosphorus has to look like this. When I translate this into my electron configuration, I get 1s2, 2s2, and then this will condense into 2p6, 3s2, and then this will condense into 3p3. Okay? So there's my orbital notation for phosphorus and my electron configuration for phosphorus, and you can copy that into your worksheet. Which then brings me up to the third example that I want to do, which is vanadium, which happens to be an element right here on the periodic table. It has an atomic number of 23. So vanadium's atomic number is 23, which means it has 23 protons and 23 electrons. Now, with every electron configuration or every orbital notation, we are always going to start with the same process, so we're always going to start at 1s. So I'm going to write 1s, and I'm going to go arrow up, arrow down, and then I'm going to go to my second energy level, which has two sublevels, the s and the p. So 2s, 2p, 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 arrow up, arrow down, arrow up, arrow up, arrow up, arrow down, arrow down, arrow down. Okay, so 2, 4, 6, 8, 10 of my electrons. I have to place 13 more. So now I'm going to go into my third energy level, which is 3s, 3p, 3d. But what I want to point out here is that the 4s in this pattern comes before 3d. So the s sublevel can only hold 2 electrons. The p sublevel can hold 6 electrons. So you might be able to reason or guess that the s sublevel is smaller than the p sublevel, okay? Because the p sublevel holds 4 more electrons. And one might also be able to guess that the d sublevel is larger than the p sublevel. It's in fact so much larger than the p sublevel that it holds 10 total electrons instead of 6. So those 4 extra electrons require more space. Which brings me up to the 4s. That 4s can only hold 2 electrons, and even though it is pretty big, it's not bigger than in a sublevel that holds 10 electrons. There's some other things that come into play about the amount of energy each electron has, but for ease of understanding in terms of what we're doing today, understand that the 3d sublevel is significantly larger than the 4s sublevel because the 3d sublevel holds 8 more electrons than the 4s sublevel. So that means that I'm going to go 2s, 2p, I'm going to go 3s, arrow up, arrow down, 3p, arrow up, arrow up, arrow up, arrow down, arrow down, arrow down. And at this point, I've used 2, 4, 6, 8, 10, 12, 14, 16, 18. So I have to go into the 4s. So that's going to be 4s, which is arrow up, arrow down. And then so 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, which means I have 20 electrons left to place. And the only place to go after the 4s is into the 3d. So my 3d is 3d, 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 1, 2, 3, 4, 5. But I've only got 3 electrons left to place. And just like we did with phosphorus, we are going to spread them out. So this is my orbital notation for vanadium. My electron configuration for vanadium would be 1s2 for the 2 arrows, 2s2 for the 2 arrows. This will condense into 2p6, 2, 4, 6, and then 3s2 for the 2 arrows. This will condense down into 3p6, 2, 4, 6, and then 4s2 for the 2 arrows, and then 3d3, this will condense down like this, okay? So 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d3 is my electron configuration for vanadium. Now, I told you when we started the side quest that the entire purpose for this was to help you identify easier and faster the number of valence electrons that an atom has. And that's true. So let's go back and talk about the idea of what a valence electron is. Remember, valence electrons are the number of electrons in the outermost energy level. Of an atom. And the outermost energy level of an atom comes from this diagram here. We have our first energy level, our second energy level, our third energy level, fourth energy level, and you see the fifth one is peeking through, right? So the biggest energy level in, say, this atom right here is the third energy level, because this number right here tells me the energy level of an electron. So the third energy level in this atom has 2 electrons. So this atom, valence electrons, is equal to 2. Okay? So let's take a look at how that would relate to phosphorus. So phosphorus...
Mr. Bader, please call the office.
So phosphorus, if I look, I see here's my first energy level, here is my second energy level, and here is my third energy level. So when I look at this atom, I see that this atom has 3 total energy levels, and the biggest energy level is the third energy level. So when I ask students how many valence electrons this atom has, a lot of students will say 3, and I will say wrong, and they will say huh, and I will say the third energy level is this whole thing right here, which means it's 1, 2, 3, 4, 5 valence electrons. So when we're looking at valence electrons, we're looking for the large number here, which is your principal quantum number, and then we're going to combine the number of electrons that are in that if it happens to show up more than once. Okay? Let's take a look at vanadium. So here I have vanadium. I have a much larger orbital notation and electron configuration here. And so when we look at valence electrons here, okay, I ask students, and some students start adding things up, and then I stop them and I say that my largest energy level is the fourth energy level, so this has 2 valence electrons. Okay. So that's helpful in terms of finding the number of valence electrons, which is easier than doing it the way we were doing it before. So when we were doing it before, we were drawing Bohr model diagrams, right? So our Bohr model diagram for like an atom like magnesium might have looked something like this. So we have our nucleus, and around the nucleus in that first energy level, we would have 1, 2 electrons. Oh wait, this is my first energy level, and it's got 2 electrons, and the first, oh, that's pretty cool. And then we're gonna go here in our second energy level, and if you remember when we drew Bohr diagrams, the second energy level could only hold 8. So 1, 2, 3, 4, 5, 6, 7, 8. And look, my second energy level, 2 plus 6 is 8. Wild. And then I'm going to draw my third energy level, which you might recall can hold up to 18, but right now I've only got 2, so I'm going to draw 1, 2. Okay, so this outer energy level here told me that these 2 electrons were also how I would determine the number of valence electrons in an atom. And the problem is that I can't always draw Bohr diagrams for everything. Like, that just seems like a lot. So let's take a look at where magnesium is on the periodic table. Magnesium is right here in the second column of the periodic table, and it has 2 valence electrons. And one of the things that we know about elements on the periodic table is that the elements in the columns tend to have similar chemical properties, or physical properties as well. So I could guess then that magnesium has if magnesium has 2 valence electrons, calcium would have 2 valence electrons, strontium would have 2 valence electrons. And look, when I look back at here, its electron configuration ends with 3s2. Now, another thing I want to point out here is that for our periodic table, we kind of talked about this already. There are 1, 2, 3, 4, 5, 6, 7 rows of my periodic table, right? And then people are like, well, what about these guys down here? And I'm going to say, well, hold on a second. So we'll come to those guys in a second. But if I look at my first row of my periodic table, there are 2 atoms, an atom that has 1 electron and an atom that has 2 electrons. And if an atom has 1 electron or an atom has 2 electrons, that means that its electron configuration would be 1s2 or 1s1, right? So in this case, I know that the atoms that end their electron configuration with an S are going to be somewhere in this general region right here. And we refer to this general region right here as something called the S block. Okay, with this as an exception, or in addition, okay? So I know that every electron configuration in this column will end something S1, and and this column will end something S2, okay? So that tells me something about the properties of these atoms right here. And I've also already identified that magnesium has 2 valence electrons. I should probably do it in black. 2 valence electrons, right? And I've also said that calcium has 2 valence electrons, and I'm going to tell you strontium and barium do as well. Now, if we look at an element like phosphorus, for example, phosphorus ends its electron configuration in the 3rd energy level, okay? And there's 1, 2, 3, 4, 5, 6. No, or 1, 2, 3, 4, 5. No, kind of hold on here. If I say that 1s2, because we have 2 electrons in the 1st energy level, 2s2, oh look, here's this. So now I'm here on my periodic table, 2p6, 1, 2, 3, 4, 5, 6, and I go back to 3s2, and then I go to 3p3, 1, 2, 3. What I'm getting at here is that this section of the periodic table will always be referred to as the P block. Okay, and what this really tells me is that any atom that has that its electron configuration ends in this general region right here could end with P1 or P2 or P3 or P4 or P5 or P6. Okay, now here's the thing that's kind of important. If we're looking at phosphorus, and I just told you that phosphorus, we identified phosphorus as having 5 valence electrons, because of it being in the 3rd energy level, 1 sp2 or s2 and p3, that means that this has 5 valence electrons. And if phosphorus has 5 valence electrons, well then arsenic is going to have 5 valence electrons. So really everything in this column is going to have 5 valence electrons. So let's go back to vanadium. Okay, now vanadium is a little bit trickier because we go into that 4s overlap. So 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and now I'm going to tell you that this is 3d123. So this is an element that's in the D block of the periodic table, which we could refer to here like so. So I'm going to say that every element in here is the D block. Okay, and any element that ends its electron configuration in this column would be D1 or D2 or D3 or D4 or D5 or D6 or D7 or D8 or D9 or D10. Now, here's the thing. If vanadium has a D sublevel, right? And I go back and look at vanadium. Here's the vanadium's D sublevel. And we said that the number of valence electrons in vanadium had to be 2 because the highest energy level was the 4th energy level. That's where this overlap comes into play. So that's how this works. So this is part of the 3rd sublevel. This is part of the 4th sublevel, the 5th sublevel, and the 6th sublevel. Okay, and then we have another part down here that's even, and then so like really when you're in this general area right here of the D block, locating the number of valence electrons, you probably are going to have to go back to the S block or maybe the P block, depending on the type of atom, but most likely you're going to go back to the S block to figure out what the valence electrons are. And then when you go down to this bottom part down here, this is called the F block of the periodic table. okay? Because anything in this part of the periodic table will end its electron configuration with F1, F2, F3, F4, F5, F6, F7, F8, F9, F10, F11, F12, F13, and F14, because the F block can hold the F sublevel can hold 14 electrons. So what I'm getting at here is that the columns tell you something that's really important. And the other thing I'm going to kind of tell you is that if this ends with S1 or this ends with S1, I can tell you that this has everything in this column is going to have one valence electron. And everything in this column, if it goes 2s2, 2p1, that means that this is going to have 3 valence electrons. And 2p2 is going to have 4 valence electrons. And we just talked about this column, and if you want to guess, this is going to be 6 valence electrons and 7 valence electrons, and these are all going to have 8 valence electrons going down, with the exception of this one, which will have 2 valence electrons. So there it is. That's how it works. If you have any other questions, please let me know. Otherwise, good luck completing the worksheet.